Somewhere above the clouds tonight, if you stepped outside and looked toward the western horizon just after sunset, you would probably see a single steady point of light, brighter than anything else in the sky except the moon. People have called it the evening star for as long as anyone has kept records. And in the morning, before the sun rises, that same point sometimes reappears on the other side of the sky. And people called it the morning star, not realizing for a long time that it was the same object. That object is Venus, the second planet from the Sun, and it is close enough to Earth in size, mass, and composition that for most of the 20th century, scientists quietly assumed it had to be some version of a warmer, wetter version of home. It took decades of failure, a string of destroyed spacecraft, and a handful of stubborn engineers willing to try again after almost every attempt ended in silence, before anyone actually learned what was waiting under those clouds. This is the story of how we found out, and of what we still do not fully understand about the planet next door for most of human history. Venus was simply a bright light with no depth to it. Ancient Babylonian astronomers tracked its movements with real precision more than 3,000 years ago, recording its rising and setting in cuneiform tablets that survive today. The ancient Greeks, before they understood it was a single body, gave it to separate names, thinking the morning and evening appearances were two different stars. It was only later, as understanding of the solar system matured, that astronomers realized this brilliant point was a planet orbiting the Sun on a path closer in than Earth's own orbit, which is why it never strays far from the Sun in our sky and why it always appears near sunrise or sunset. When Galileo Galilei turned one of the earliest astronomical telescopes toward Venus in the year 1610, he made an observation that quietly helped settle one of the largest scientific debates of his era. He noticed that Venus displayed a full set of phases, much like the moon does, cycling from a thin crescent to a fully illuminated disk and back again over the course of months. This was significant because a model of the universe, with Earth fixed at the center, with the Sun and all other planets circling around it, could not easily explain a full range of phases for Venus. A Sun-centered model, in which Venus orbits the Sun on a path inside Earth's own orbit, explained the observation naturally. Galileo's phases of Venus became one of the pieces of observational evidence that helped tip scientific opinion firmly toward a heliocentric view of the solar system, at a time when that idea was still genuinely controversial and, in Galileo's own case, personally dangerous to hold publicly. More than a century later, Venus became central to an entirely different scientific problem, this time involving simple measurement rather than cosmic architecture. Astronomers in the 1700s understood the relative spacing of the planets reasonably well, but they lacked a reliable, absolute measurement of the true physical distance between the Earth and the Sun, a value now called the astronomical unit, which serves as a foundational yardstick for measuring distances throughout the rest of the solar system. The astronomer Edmund Halley proposed a clever method for calculating this distance by carefully timing rare events called transits of Venus, occasions when Venus passes directly between the Earth and the Sun, appearing as a small dark dot slowly crossing the Sun's bright disk. By recording the precise timing of this transit from multiple widely separated locations on Earth, astronomers could use basic geometry, essentially a form of parallax, to calculate the true distance to the Sun. Transits of Venus are genuinely rare, occurring in pairs roughly 8 years apart, with more than a century typically separating each pair. This led to major international scientific expeditions, organized around the transits of 1761 and 1769, sending astronomers to remote locations around the globe, including the South Pacific, specifically to observe and time these events. Captain James Cook's first voyage to the Pacific in 1768 was funded and organized substantially around the goal of observing the transit of Venus from the island of Tahiti. These international observational campaigns, despite various practical difficulties in timing the exact moments of contact precisely, produced the first reasonably accurate measurement of the astronomical unit, a foundational achievement in the history of astronomy that came directly from careful, patient observation of Venus crossing the face of the Sun, when telescopes became powerful enough to resolve Venus as a disk rather than a point. Astronomers found something frustrating. Mars has visible surface features. Jupiter has bands and a great red storm. Venus has nothing. Every telescope, in every era, looking at Venus, saw only a featureless, brilliant white ball. This blankness became one of the defining mysteries of planetary science for centuries. The obvious explanation was clouds, thick enough to hide everything beneath them permanently. And that explanation turned out to be correct, but it opened up a much larger question. If nobody could see through those clouds, nobody could know what the surface actually looked like, or what conditions existed down there. Into that gap, scientists built a model based on reasonable but ultimately mistaken assumptions. This scientific picture, however tentative, filtered directly into popular culture throughout the middle decades of the 20th century. Science fiction writers of the era, drawing on the genuinely uncertain scientific consensus of their time rather than pure invention, frequently portrayed Venus as a humid, swampy, jungle-covered world, sometimes populated by exotic plant life or primitive creatures adapted to a hot, wet climate. These portrayals were not simply fanciful guesses. They reflected the best available scientific thinking of their day fairly faithfully, which makes them a useful historical record of just how confidently the wet Venus model was held, even though it would later be shown to be almost completely wrong in every practical respect. It is a useful reminder that scientific consensus, even when reasonably argued and broadly accepted, remains provisional and can be overturned entirely by a single well-placed measurement, as Mariner 2's radiometer would go on to demonstrate only a few years later. The reasoning went something like this. Venus is almost exactly the same size as Earth, only slightly smaller in diameter and slightly less massive. It has roughly similar bulk composition. It sits closer to the Sun, so it should be warmer, but not unimaginably so, because thick white clouds should reflect a great deal of sunlight back into space before it ever reaches the ground. Astronomers reasoned that beneath that reflective cloud layer, sunlight would be dim, temperatures would be humid, and the ground could easily be covered in swamps, oceans, or dense tropical vegetation. Popular science writing throughout the 1930s, 40s, and 50s leaned into this idea heavily. Venus was described as Earth's tropical twin, a planet perhaps one geological age behind our own, still working through the humid, swampy conditions that Earth itself may have passed through hundreds of millions of years earlier. Some scientists speculated about oceans of carbonated water. Others imagined dense jungles, or even primitive life forms swimming beneath a permanent overcast sky. This wet, swampy model was not fringe thinking. It was close to scientific consensus, and it directly shaped how space agencies designed their earliest missions. When the Soviet Union began building probes to send to Venus in the early 1960s, They included instrumentation specifically designed to detect and measure liquid water. On the assumption that the lander might genuinely touch down in mud, shallow water, or wet ground, engineers debated whether a probe might need to float. This tells you how seriously the swamp hypothesis was taken at the highest levels of aerospace engineering, not as an idle guess, but as a real design constraint. The first real correction to this story came not from a lander at all, but from a flyby. In August of 1962, NASA's Mariner 2 spacecraft passed within about 34,000 kilometers of Venus, becoming the first spacecraft from Earth to successfully complete a flight past another planet. It did not carry a camera capable of imaging the surface, since nothing could see through the clouds anyway, but it carried a microwave radiometer, an instrument that could measure the temperature of thermal radiation coming from the planet, even without seeing through the atmosphere in visible light. What Mariner 2 found did not fit the swamp model at all. The radiometer measured a surface temperature far higher than anything a humid greenhouse world should produce, more consistent with molten lead than with a rainforest. This was the first hard evidence that something about the accepted picture of Venus was deeply wrong, and it set off a scramble to understand why a planet so similar to Earth in size could be so violently different in conditions. Interestingly, some of the theoretical groundwork for understanding this result had actually been laid a few years earlier, before Mariner 2 ever flew. In the early 1960s, the young astronomer Carl Sagan, along with a small number of other researchers studying strong microwave emissions coming from Venus, proposed that these emissions could be explained by an extremely hot surface trapped beneath a thick, insulating blanket of carbon dioxide, essentially predicting a runaway greenhouse effect on theoretical grounds before any spacecraft had confirmed it directly. This was one of several competing explanations circulating at the time, including alternative proposals suggesting the strong radio emissions might instead originate from electrical activity high in the atmosphere rather than genuine surface heat. Mariner 2's direct radiometer measurements helped settle this particular scientific disagreement in favor of the hot surface interpretation, giving early, credible confirmation to what had been, up to that point, only one hypothesis among several. It is a useful reminder that major discoveries in planetary science often arrive gradually, built from theoretical prediction, competing hypotheses, and slowly accumulating observational evidence, rather than from a single dramatic moment of revelation. The United States continued its own program of Venus exploration through the 1970s as well, running in parallel with the Soviet Venera missions, though following a different strategy. Rather than repeatedly attempting to land armored probes directly on the surface, NASA's Pioneer Venus program, consisting of 2 separate spacecraft launched in 1978, focused on a broader atmospheric and orbital survey. The Pioneer Venus orbiter entered orbit around the planet and spent more than a decade studying the upper atmosphere, cloud structure, and surface topography using radar altimetry, providing the first reasonably detailed global map of Venusian surface elevation, even though its radar resolution was far coarser than what later missions would achieve. The companion spacecraft, known as the Pioneer Venus Multiprobe, released a set of 4 separate descent probes, 1 larger probe and 3 smaller ones, timed to enter the Venusian atmosphere at different locations simultaneously. None of these probes were designed to survive an actual landing, since they carried no cameras and had not been armored in the way Soviet landers were, but each was instrumented to measure atmospheric composition, temperature, and pressure continuously during its descent. Remarkably, one of the small probes not designed to survive impact at all, continued transmitting data for a short period even after reaching the surface intact. An unplanned bonus that briefly extended the mission's scientific return. Together, these measurements from the Pioneer Venus probes complemented the ground-level Soviet data closely, confirming atmospheric composition and structure at multiple different locations around the planet, rather than at only the isolated landing sites the Venera landers had reached. The explanation, once scientists worked it out, involved a process now called the runaway greenhouse effect, and it remains one of the most important concepts in all of planetary climate science, partly because it may be relevant to Earth's own distant future, and partly because it directly informs how scientists think about the habitability of planets around other stars. On Earth, the atmosphere contains greenhouse gases like carbon dioxide and water vapor that trap a certain amount of outgoing heat, warming the surface to a comfortable range. This effect is delicately balanced. If Earth had no greenhouse gases at all, its average surface temperature would sit around -18 degrees Celsius, a frozen ball. Because of the greenhouse effect, we instead average around 15 degrees Celsius, comfortable enough for liquid water and life. Venus experienced a version of this same process that spiraled completely out of control. Because Venus sits closer to the Sun, its surface once received more solar heating than Earth's. As it warmed, any early oceans or surface water would have evaporated more aggressively into the atmosphere, and water vapor is itself a powerful greenhouse gas. More water vapor meant more trapped heat, which meant more evaporation, which meant even more trapped heat. This feedback loop did not stop until, in the case of Venus, nearly all of the water in the system had evaporated into the upper atmosphere, where solar ultraviolet radiation split the water molecules apart, and the lighter hydrogen atoms escaped into space over billions of years, permanently and irreversibly removing water from the planet. One reason Earth avoided the same fate that befell Venus involves a slow, self-correcting geological process called the carbonate-silicate cycle, sometimes described informally as Earth's long-term climate thermostat. On Earth, carbon dioxide in the atmosphere dissolves into rainwater and reacts chemically with certain silicate rocks at the surface, a process called weathering, which locks carbon into solid mineral form. Rivers eventually carry these minerals to the ocean, where they settle and, over very long timescales, get pulled down into the mantle at plate tectonic boundaries, only to be released back into the atmosphere later through volcanic activity, completing a slow cycle that takes hundreds of thousands of years to run its full course. Crucially, this cycle runs faster when the planet is warmer, since warmer temperatures increase rainfall and chemical weathering rates, which pulls more carbon dioxide out of the atmosphere and cools the planet back down. And it runs slower when the planet is colder, allowing volcanic carbon dioxide to build back up again. This feedback loop has helped keep Earth's climate within a relatively survivable range across enormous stretches of geological time, despite the Sun itself gradually growing brighter over billions of years. Venus, lacking plate tectonics in the same form, and having lost essentially all of its liquid water very early in its history, has no equivalent mechanism to continuously recycle carbon back into its interior. Once its runaway greenhouse effect took hold and its water was lost to space, there was no remaining feedback process capable of pulling the resulting carbon dioxide back out of the atmosphere, allowing the gas to simply accumulate over geological time into the crushing, permanent blanket that exists today. What remains today on Venus is an atmosphere made up of roughly 96% carbon dioxide, an incredibly effective greenhouse gas, with a surface atmospheric pressure about 90 times greater than Earth's, which is roughly equivalent to the water pressure you would experience about 1 kilometer beneath the ocean surface. That thick blanket of carbon dioxide traps solar heat so effectively that Venus, despite its clouds reflecting a large share of incoming sunlight back into space, ends up with a hotter surface than Mercury. Even though Mercury is much closer to the Sun and lacks any meaningful atmosphere to shield it, the surface of Venus sits at approximately 475 degrees Celsius, hot enough to melt lead, zinc, and tin, and hot enough to destroy nearly any electronic equipment humans had built by the middle of the 20th century almost instantly, named simply after the Russian word for Venus, began sending probes toward the planet starting in the early 1960s, and for years almost nothing worked. Venera 1, launched in 1961, lost contact with ground control before it even reached the planet, due to a malfunction in its orientation system, and it silently flew past Venus without returning any data. Venera 2 and Venera 3, launched in 1965, suffered similar fates, losing communication before completing their missions, with Venera 3 becoming the first human object to strike another planet's surface, though it had already gone silent and could not transmit anything about what it found. These early losses were frustrating but not entirely surprising given how new interplanetary travel still was at that point in history. The real turning point, in terms of what humanity understood about the planet, came with Venera 4 in 1967. At the time, Venera 4 was designed and built. The best available models suggested that the surface pressure of Venus was somewhere around 20 times that of Earth. This was considered high, but manageable, and the probe's descent capsule was engineered with reinforced construction to withstand pressures in that general range. When Venera 4 reached Venus and began its descent through the atmosphere, it deployed a parachute as planned, expecting a slow, controlled drift down toward the surface over the course of roughly an hour. It never reached the ground. Telemetry from the probe stopped at an altitude of approximately 27 kilometers above the surface, still high in the atmosphere by any reasonable estimate. The pressure vessel had not burned up. It had been physically crushed by atmospheric pressure that already exceeded its designed structural limits, at an altitude where engineers had expected conditions to still be relatively mild. This failure was, in its own way, an enormously important discovery, because it proved that the accepted model of Venus's atmosphere was badly incomplete. The real surface pressure was not 20 times that of Earth. It was closer to 90 times, more than 4 times higher than anyone had planned for. With a limited launch window before the next opportunity to send probes toward Venus in 1969, Soviet engineers did not have time to completely redesign the pressure vessel from scratch. Instead, they tried a different approach for the next 2 probes, Venera 5 and Venera 6. Their idea was to reduce the size of the parachute, reasoning that a faster descent would spend less time in the punishing upper atmosphere, potentially allowing the probe to reach the ground before heat and pressure destroyed it. This approach also failed. Both probes were crushed at an altitude of roughly 11 kilometers above the surface, a little further down than Venera 4 had managed, but still nowhere close to the ground. This forced a complete rethink for the next probe, Venera 7, and the redesign that followed represents one of the more remarkable engineering pivots in the history of planetary exploration. The engineers essentially abandoned the idea of building an aerospace vehicle and instead began designing something closer to a deep-sea submarine. The new descent capsule featured a forged titanium sphere, capable of withstanding pressures of around 180 atmospheres, roughly double what scientists now believed the actual surface conditions to be, giving the design a generous safety margin after 2 consecutive humiliations. To save weight for this heavier armor, the engineers stripped out almost every scientific instrument they could remove. There were no windows. The solar panels, which would have been useless anyway given how little direct sunlight reaches the ground on Venus, were replaced with a heavy internal battery. Venera 7 launched in August of 1970, and its descent did not go entirely to plan even then. During the final stage of descent, the parachute's reefing cords melted in the intense heat, causing the parachute to fail. Rather than floating gently down, the probe fell, striking the surface at a velocity of roughly 17 meters per second, a hard, uncontrolled impact. In mission control, the telemetry signal went flat almost immediately, and the mission was initially logged as a failure, just like the ones before it. It was only during a later review of the raw radio tapes that an astronomer noticed something odd buried in what looked like random static. The probe had not died on impact after all. It had tipped over onto its side during the crash, pointing its antenna away from Earth rather than toward it, which weakened its signal dramatically but did not eliminate it entirely. By carefully processing this faint, garbled transmission, engineers were able to recover approximately 23 minutes of temperature data sent from the surface of Venus. It was the first time in history that a human-built machine had transmitted data from the surface of another planet, and the data confirmed a surface temperature of roughly 475 degrees Celsius, matching what Mariner 2's radiometer had suggested years earlier from orbit. Venera 7 proved that a sufficiently armored titanium sphere could survive the crushing pressure at the Venusian surface. It did not solve the problem of the extreme heat, which remained a separate and equally serious engineering obstacle. The surface temperature of Venus is hot enough to melt lead, zinc, and tin, and hot enough to destroy the silicon-based electronics used in nearly all mission hardware almost instantly upon exposure. Simple insulation could only delay the inevitable, since insulation slows heat transfer but does not stop it permanently, and eventually the heat finds its way in. Active cooling systems using fans or radiators, the kind used in many other engineering applications, were also useless on Venus, because a radiator works by dumping excess heat into cooler surrounding air, and on the Venusian surface, the outside air is hundreds of degrees hotter than the machinery it would supposedly be cooling. The solution that Soviet engineers eventually settled on turned each lander into something like a temporary heat sink, engineered to absorb a fixed, finite quantity of heat before failing, rather than trying to resist heat indefinitely. Before a lander separated from its orbiter, cold liquid was circulated through the pressure vessel, chilling the internal components down to roughly -10 degrees Celsius, well below freezing. This gave each probe a thermal head start, effectively sending it into the Venusian atmosphere as a block of ice descending into a furnace. To manage the heat that would inevitably build up during descent and after landing, engineers packed the interior with a phase change material, specifically lithium nitrate, a chemical compound with a melting point of about 30 degrees Celsius. When a substance melts, it absorbs a large quantity of thermal energy without its own temperature rising further, at least until the melting process is complete. As heat from the Venusian atmosphere worked its way through the titanium shell, that energy went into melting the lithium nitrate rather than immediately frying the sensitive electronics inside. This bought each lander somewhere between 50 and 60 minutes of functional operating time on the surface before the cooling system was overwhelmed and the interior temperature climbed past survivable limits before any of these thermal and pressure systems even came into play. Each lander first had to survive the atmospheric entry phase itself, decelerating from an interplanetary approach speed of several kilometers per second down to a survivable descent speed within a matter of minutes. This deceleration subjected the spacecraft and its instruments to enormous mechanical stress, with peak forces during entry reaching somewhere in the range of 350 times the force of gravity on Earth for some of the Venera probes, a level of sustained force that would be instantly fatal to a human being, and that pushed the structural engineering of the descent capsule to its absolute limits before the vehicle had even begun to experience the atmosphere's crushing pressure or extreme heat. Surviving this initial entry phase intact, with all instruments still functioning afterward, was itself a significant engineering achievement that is easy to overlook next to the more dramatic later stories of heat and pressure failures. But every successful Venera landing depended on getting this violent, compressed first phase of the descent exactly right before anything else could matter. Designing a camera capable of surviving these conditions required an entirely different approach from ordinary photography. Television cameras of the 1970s relied on cathode ray tube technology and glass lenses, both of which are fragile and would have cracked instantly under the external pressure if placed anywhere near the outer surface of the pressure vessel. Engineers could not risk installing a large glass window in the side of the sphere, since any structural failure there would cause the entire vessel to implode immediately. Instead of a conventional camera, they built what is called a telephotometer, a mechanical scanning device rather than a lens-based imaging system. The delicate parts of the telephotometer remained safely sealed inside the cooled titanium sphere, and it looked out at the world only through a small cylindrical window made of thick quartz, strong enough to withstand the external pressure while still allowing light through. The mechanism itself was mechanically simple, which was precisely the point, since simplicity meant fewer components that could fail under extreme stress. A small mirror rotated back and forth behind the quartz window, sweeping across the scene outside and collecting light from one narrow point on the ground at a time, directing that light into a sensor that measured its brightness. The mirror then shifted slightly and repeated the process for the next point, building up an image one measured dot at a time rather than capturing an entire scene in a single instant the way a photographic camera does. The probe transmitted this stream of individual brightness measurements back to Earth as raw telemetry data, not as a video signal, and it fell to ground-based computers to reconstruct the image, line by line, from that long string of numbers. This method was inherently slow, often requiring many minutes to build a single complete panoramic image. And if the probe overheated and failed before a scan finished, the resulting image would simply cut off partway through, an incomplete window onto an alien landscape. The trade-off, though, was durability. Engineers judged, correctly, that a slow mechanical scanning eye had a far better chance of surviving Venusian conditions than a more complex electronic imaging system. On October 22, 1975, the lander Venera 9 reached the surface of Venus and survived long enough to transmit data for approximately 50 minutes. A substantial improvement over the 23 minutes Venera 7 had managed 5 years earlier. It touched down on a slope of roughly 20 degrees, on ground scattered with what would soon turn out to be an unexpectedly rocky landscape. Engineers had prepared for what they believed was the worst realistic case regarding visibility at the surface, because the atmosphere was 90 times denser than Earth's. Many scientists had predicted that little or no sunlight could penetrate all the way down to ground level, meaning the surface might exist in near total darkness, similar to conditions at the bottom of a deep ocean. To guard against this possibility, the lander carried powerful floodlights intended to illuminate the ground directly in front of the camera. When the lens cover popped away after landing, sensors immediately detected ambient light. The floodlights turned out to be unnecessary. The surface of Venus was not dark at all. Ambient light levels at the ground were comparable to an overcast, cloudy day back on Earth, since the thick atmosphere scattered incoming sunlight evenly in every direction, producing a soft, diffuse glow rather than harsh shadows, but still providing plenty of usable light for the telephotometer to work with. The scan took about 30 minutes to build a complete panorama, and when the data arrived back on Earth, scientists saw something that directly contradicted years of accepted theory. Given how dense the atmosphere was, many researchers had expected persistent, powerful winds at the surface, strong enough to grind exposed rock down into fine sand or smooth pebbles over geological time, the way sustained sandblasting erodes stone on Earth. Instead, the images from Venera 9 showed a surface covered in sharp, angular rocks with jagged, unworn edges. This told scientists two important things at once. First, the surface appeared to be geologically young, since these rocks had clearly not been sitting exposed to erosive forces for very long. Second, and just as significant, actual wind speeds at ground level had to be quite low, despite the crushing density of the overlying atmosphere, because the rocks showed essentially no signs of wind erosion. The images also revealed unusually clear air near the ground itself, with no fog or airborne dust obscuring the view, allowing the horizon to be seen clearly in the corners of the panoramic frame. The probe appeared to be resting on a scattered pile of debris, possibly disturbed by the landing itself or by some recent localized geological shift in the terrain. 3 days later, its twin, Venera 10, landed more than 2,000 kilometers away and operated on the surface for about 65 minutes, touching down on noticeably older, smoother terrain. Its images showed flat slabs of rock resembling solidified, weathered lava flows, quite different in character from the jagged debris field at the Venera 9 site. Taken together, these two landings proved something important about the planet as a whole. Venus was not a single, uniform wasteland with identical conditions everywhere. It had distinct geological regions, including mountains, slopes, and broad plains, each shaped by different histories of volcanic activity, tectonic stress, and age. Still, the single most striking scientific finding from these missions remained the light itself. The simple, unglamorous fact that enough diffuse sunlight penetrated 90 atmospheres of carbon dioxide to make photography possible at all, directly overturning earlier predictions of total, permanent darkness at the surface. These two black and white panoramas represented the first direct images ever captured of the surface of another planet, an extraordinary achievement, but they remained limited in one obvious way. Scientists could see the shapes and textures of the Venusian landscape, but without color information. They could not directly see the chemical character of the world they had touched, since color in planetary imaging often carries clues about mineral composition and atmospheric filtering effects. Between these missions, A few other Venera landers deserve mention, even though they did not carry cameras themselves. Venera 8, which landed in 1972, 3 years before Venera 9, was primarily focused on measuring light levels and soil composition rather than imaging, and its light sensor provided the first direct measurement suggesting that meaningful sunlight did reach the surface. An early hint of what Venera 9 would later confirm with actual photographs. Venera 8 also carried a simple gamma-ray spectrometer, capable of estimating the general chemical character of surface rock without a full imaging system, and its measurements suggested a composition broadly similar to granite in some respects. An early clue that Venusian geology might be more chemically varied and Earth-like in places than a purely simple, uniform picture would suggest, leaving both probes blind despite having fully functional telephotometers underneath. Despite this repeated setback, these two missions still returned valuable data on atmospheric composition and became the first Venera landers to detect what appeared to be electrical discharges consistent with lightning activity in the clouds above, a finding that added early fuel to the lightning debate mentioned earlier. Since these detections came from onboard electromagnetic sensors rather than direct visual observation of any actual flash, that gap would not be closed for another 7 years. In March of 1982, the Soviet Union launched what many consider the high point of the entire Venera program. The missions known as Venera 13 and Venera 14. These probes were heavier, carried more sophisticated instrumentation, and were built with the accumulated lessons of every prior mission behind them. The scientific goal had shifted. It was no longer enough to simply prove that a probe could survive and return an image. The new objective was to characterize the Venusian surface chemically as well as visually, in far greater detail than before, to capture color. Engineers upgraded the telephotometer design so that it could scan the same scene multiple times using red, green, and blue filters in sequence, with the resulting 3 separate data streams later recombined on Earth into a single composite color image, similar in principle to how some early color photography techniques worked. Venera 13 landed on March 1st, 1982, and survived on the surface for a record 127 minutes, more than twice as long as any previous lander, giving its instruments an unusually generous window of operation. It began its scanning sequence almost immediately after touchdown. The resulting color images were genuinely startling to the scientists reviewing them. The black and white photographs from 1975 had shown a stark, textured, rocky world, but without any sense of its true coloring. The new color images revealed a landscape bathed entirely in a deep, suffocating orange glow. There were essentially no other colors visible anywhere in the scene. The rocks appeared orange. The sky appeared orange. The horizon appeared orange. This was not any kind of camera malfunction or transmission error. It was a direct consequence of atmospheric physics. The atmosphere of Venus is so thick and so heavily filled with sulfur-based aerosols and haze in its upper layers that it functions as an enormous natural color filter, absorbing much of the blue and green wavelengths of sunlight before they ever reach the ground, and allowing mostly red and orange wavelengths to pass through to the surface. To confirm this interpretation rather than assume it, the lander carried a small color calibration chart within the camera's field of view, printed with reference strips of white, red, green, and blue paint whose true colors were precisely known in advance. In the transmitted image, the white reference strip appeared distinctly orange, and the blue reference strip appeared almost completely black. providing direct proof that a human being standing on the surface of Venus would perceive the entire world in shades of a single warm, muted tone, something close to sepia, and that the human eye and brain would have no way to correct for this shift, since there would be no source of true white light anywhere in the environment to use as a reference point. Venera 13 also achieved something else entirely new in the history of planetary exploration. It carried an instrument called a Groza microphone, originally designed to detect seismic activity and electrical discharges in the atmosphere, but which also functioned as a straightforward audio recorder. It captured the first sounds ever recorded on the surface of another planet. The resulting recording revealed two distinct categories of noise. The first was simply wind. Telemetry data indicated a surface wind speed of only about 0.5 meters per second, a speed that on Earth would barely register as a light breeze, unable to move a leaf. On Venus, however, the atmosphere is roughly 60 times denser than Earth's air at similar conditions, and a dense fluid moving even slowly carries far more force and momentum than a much lighter fluid moving at the same speed. The microphone picked up a low, steady, aerodynamic drone caused by this thick atmosphere flowing continuously around the structure of the lander. The second sound captured was mechanical rather than atmospheric. The probe successfully deployed a pneumatic drill to collect a small sample of surface material for chemical analysis. The microphone recorded the sharp, explosive sound of a pyrotechnic charge firing to activate the drilling mechanism, followed by the grinding noise of the drill bit cutting into basaltic rock beneath the lander. Together, this audio confirmed something scientists had suspected but not directly measured: that the dense Venusian atmosphere is an unusually effective conductor of sound, and that the surface environment, far from being silent, was in a real sense a loud one, filled with the sounds of wind and machinery alike. Venera 14 landed for days after its twin. On March 5, 1982, touching down in a flatter, smoother region roughly 1,000 kilometers from the Venera 13 site, on terrain resembling cracked pavement made of basaltic rock. Its mission objectives mirrored those of Venera 13 closely, including photographing the surface, analyzing atmospheric chemistry, and physically testing the mechanical properties of the ground using a spring-loaded arm. This arm was designed to swing outward from the base of the lander and strike the surface with a precisely known force, allowing scientists to calculate the physical density and compressibility of the Venusian soil simply by measuring how far the arm penetrated on impact. A straightforward mechanical experiment meant to reveal whether the ground was soft, loose material, or solid, unyielding rock. The landing sequence proceeded automatically in a fixed order. First, the lander secured its footing on the surface. Then the cameras began operating. During descent, the camera lenses had been protected by titanium caps, shielding the delicate optics from extreme heat and pressure on the way down. Once safely on the ground, small pyrotechnic charges fired to eject these protective caps, clearing the view for the telephotometers underneath. On Venera 14, the ejection mechanism worked exactly as designed, but the discarded cap did not roll away from the lander the way engineers had hoped. Instead, it happened to land directly on the one small patch of ground where the compressibility arm had been programmed to strike. A short time later, the arm deployed as planned and swung down, striking the object sitting directly beneath it with its full calibrated force. The telemetry sent back to Earth indicated an almost impossibly hard, rigid surface, showing essentially zero compressibility. Results that did not match expectations for loose surface material at all. This turned out to be technically accurate data about the wrong object entirely. The probe had not measured the soil of Venus. It had measured the titanium lens cap it had itself carried down from Earth and inadvertently dropped in exactly the wrong spot. The onboard camera scanned the surrounding area and returned an image, confirming the mistake clearly, showing the mechanical arm pressed firmly down against the center of its own discarded equipment, with the actual, untouched surface of Venus visible only centimeters away, tantalizingly out of reach. This incident remains one of the most well-known mechanical mishaps in the history of planetary exploration, not because it reflected poorly on the engineers, but because of what it illustrates about the sheer difficulty of remote operations on another world. A team of scientists and engineers had successfully guided a spacecraft across tens of millions of kilometers of empty space, survived a punishing descent through one of the most hostile atmospheres in the solar system, and landed safely on a planet hot enough to melt lead, only to have one specific measurement thwarted by a small piece of their own equipment landing in exactly the wrong place at exactly the wrong moment, for roughly 30 years. Afterward, the mission data from Venera 13 and 14 sat quietly in scientific archives, largely considered a closed chapter. The broader scientific consensus about Venus by this point held that the planet was completely sterile, since its surface temperature and pressure made any conventional form of organic chemistry effectively impossible. In 2012, however, a paper published by the planetary scientist Leonid Kassanfomality challenged this settled view, at least in a limited and highly specific way. Kassanfomality was not a fringe outsider making wild claims from the sidelines. He had been a respected contributor to the original Soviet space program and had direct professional familiarity with the mission data he was now revisiting, using modern digital image processing techniques that were simply unavailable in the 1980s. He went back and re-examined the raw panoramic image sequences returned by Venera 13. His analysis focused specifically on the timeline of these images, because the telephotometers had not captured a single instantaneous snapshot the way a modern camera does. Instead, they had scanned the same general scene repeatedly over the full duration of the lander's operational life, building up a slow sequence of overlapping images across more than 2 hours. By carefully aligning these sequential scans and looking closely for differences between them, Kassanfomality searched for anything that appeared to move or change over the course of the recording. He reported finding several such objects, features that seemed to appear, shift position, or vanish across different frames. The most widely discussed of these he nicknamed the Scorpion. In the earliest scans taken shortly after landing, the ground in that particular area appeared empty. In a scan captured roughly 7 minutes after touchdown, a distinct, structured object appeared in the frame, measuring approximately 15 centimeters in length, with what looked like a rounded central body and a curved, tail-like extension. In later scans, the object was no longer visible. Kassanfomality argued that this object had emerged from beneath the surface material, remained visible for a period of time, and then moved out of the camera's field of view entirely. He also pointed to a second feature he called the black flap, an object that appeared to change its shape and relative position across different scans. Based on these observations, he suggested, quite cautiously in his original paper, that some kind of unconventional biology, potentially based on exotic chemistry rather than the carbon and water-based chemistry familiar from Earth, might conceivably explain what the images seemed to show. Kassanfomality's paper was published in a peer-reviewed Russian astronomical journal, and he continued to defend and refine his interpretation in follow-up papers over the following years, maintaining that the objects he identified showed patterns of movement, difficult to fully explain through mechanical failure alone. This idea did not gain acceptance within the broader scientific community, and it is important to understand clearly why, since the rebuttal itself involves genuinely interesting engineering detail. Independent researchers, including scientists at NASA and other Russian institutions, proposed a straightforward mechanical explanation for the same anomalies. Each Venera lander was wrapped in multiple layers of thermal insulation and protective plastic material, necessary to help the probe survive its brief window of operation in the extreme heat. As the interior temperature of the lander inevitably rose over the course of its operating life, despite the cooling systems and phase change materials designed to slow that process, these insulating materials began to melt, warp, peel, and detach in small pieces. Reviewers argued that the apparent movement captured in the Scorpion and Black Flap images was not biological activity at all, but simply the visible result of the lander itself slowly disintegrating under thermal stress, with pieces of melting plastic and insulation shifting position between scans. The apparent changes in shape and shadow were also plausibly explained by the slowly changing angle of ambient sunlight over the course of the recording, or by the lander itself gradually settling deeper into the soft debris it had landed on. Later, more careful digital restorations of the same image sequences, conducted with even more advanced processing techniques than Casanformaletti had access to in 2012, further supported this mechanical explanation, identifying the moving features as artifacts, image noise, or genuinely detached pieces of the lander's own hardware rather than anything resembling a living organism. It is worth sitting with this story a little longer though, because even without any biological explanation, it reveals something genuinely interesting about the character of these images that is easy to miss. Despite the ultimately mundane explanation for the moving features, the underlying observation itself was correct. The surface of Venus, at least in the immediate vicinity of a dying lander, was not a static, unchanging scene. It was a dynamic, violent environment in which materials were actively shifting, debris was moving, and the machine itself was visibly groaning, warping, and slowly failing under conditions no human engineering had ever faced before. The strange, seemingly impossible shapes captured in those panoramas were very likely the final convulsions of the probe's own body, recorded in unintentional slow motion by a scanning camera that happened to still be working. As its host machine came apart around it, the camera aboard Venera 14 turned out to be the very last set of eyes humanity has ever opened directly on the surface of Venus after 1982. Soviet mission priorities shifted noticeably. Engineers and scientists recognized that landing probes in scattered, essentially random locations provided excellent detailed data about specific small patches of ground, but could never build a coherent picture of the planet as a whole. To understand Venusian geology on a truly global scale, a different observational strategy was required, one capable of seeing through the clouds from orbit rather than only from the surface. Venera 15 and Venera 16, launched in 1983, represented this shift in approach. Neither carried a lander at all. Instead, both spacecraft carried large synthetic aperture radar systems, instruments capable of penetrating the thick cloud cover entirely and mapping surface topography using reflected radio waves rather than visible light. These two orbiters together mapped the northern hemisphere of Venus in considerable detail, revealing widespread shield volcanoes, extensive lava channels, and clear evidence of tectonic fracturing across large stretches of the surface. This radar data proved scientifically invaluable for understanding Venusian geology at a planetary scale, but it produced something fundamentally different from a photograph. It generated an abstract topographic map, rich with elevation and roughness data, but entirely without the direct visual character of an actual picture taken from the ground. The final Soviet missions to Venus, known as Vega 1 and Vega 2, launched in 1985. These were unusual hybrid missions, designed primarily to intercept and study Halley's Comet during its close approach to the inner solar system, using Venus as a convenient staging point along the way. Both spacecraft dropped off landing units at Venus before continuing onward toward the comet. These Venus landers focused specifically on soil chemistry and atmospheric analysis rather than imaging, and they also deployed instrumented balloons designed to float within the upper atmosphere of Venus, measuring wind speeds and atmospheric conditions at altitude over an extended period. Notably, neither lander carried a camera at all. The two Vega balloons deserve a little more attention on their own, because they represent a genuinely different way of exploring a planet compared to everything that came before them, rather than dropping straight down toward the surface. Each balloon was designed to inflate with helium after separating from its carrier spacecraft and then drift freely within a stable layer of the atmosphere, at an altitude of roughly 54 kilometers, a region where temperature and pressure conditions are surprisingly close to those found near the surface of Earth, even though the crushing heat and pressure of the true Venusian surface lies tens of kilometers further down. Each balloon operated for a little over 2 Earth days, drifting more than 11,000 kilometers across the night side of the planet, carried along by the same powerful high-altitude winds responsible for the atmosphere's dramatic superrotation. During this time, the balloons measured wind speed, temperature, pressure, and the density of the surrounding cloud particles continuously, and their data revealed a surprisingly turbulent and dynamic environment at this altitude, including strong vertical air currents that caused each balloon to rise and fall repeatedly as it drifted. Evidence of genuine atmospheric weather occurring within the Venusian cloud layer, a finding that added meaningfully to scientists' understanding of Venus as an atmospherically active world rather than a static one. Ground-based radio telescopes on Earth, including facilities in multiple countries coordinated together for the occasion, tracked the balloons' positions throughout their flight by precisely measuring the radio signals each balloon transmitted, an approach that lets scientists reconstruct the balloons' full flight paths after the fact, even though the balloons themselves carried no cameras or imaging systems of their own. By this point in the program, engineers had judged that the weight budget available for scientific instruments was better spent on other kinds of measurements, given how much had already been learned visually from the earlier Venera 9, 10, 13, and 14 missions. With the subsequent collapse of the Soviet Union at the end of 1991, the broader Venera program came to a permanent end, and the raw mission data, recorded on magnetic tape using 1970s and 1980s technology, was placed into long-term storage over the following decades. That physical storage media began to degrade, as magnetic tape inevitably does over long periods of time, creating a real and growing risk that irreplaceable scientific data might eventually become unreadable entirely. The versions of the Venera panoramic images that had appeared in newspapers and scientific journals throughout the 1970s and 80s were often grainy, low contrast, and visually rough, since they were essentially analog reconstructions of what had originally been digital telemetry signals, processed using the comparatively limited computing technology available at the time. Beginning in the early 2000s, a new generation of researchers undertook a careful project of what might fairly be called digital archaeology, returning directly to the original raw telemetry data rather than working from these older analog reproductions. Modern computing hardware proved vastly more capable of processing subtle signal noise than the mainframe computers of the 1980s had been. Researchers were able to fill in missing or corrupted pixels, correct geometric distortion introduced by the mechanical scanning process of the panoramic mirrors, and generally recover a level of detail that had effectively been invisible in every version of these images previously published. This restoration work revealed genuinely new detail in the texture of the surface soil and the layering visible in exposed bedrock, and even adjusted scientists' understanding of how far away the visible horizon actually sat in these panoramas, refining measurements that had stood essentially unchanged since the original missions. Today, these carefully restored Venera images remain the only direct, ground-level optical photographs ever captured of the actual surface of Venus. Every other image of Venus that most people have ever seen is something different. Either a radar-based topographic map, an artist's rendering based on scientific data rather than a real photograph, or an image of the planet's outer cloud tops taken from orbit, which reveals atmospheric structure but tells us nothing directly about the ground far below. Subsequent missions have added meaningfully to our understanding of Venus without directly replacing this ground-level visual. Record Japan's Akatsuki orbiter, which finally achieved orbit around Venus in 2015 after an earlier failed insertion attempt, has spent years studying the planet's atmospheric dynamics and cloud structure in detail. The spacecraft's original arrival attempt in 2010 failed when its main engine malfunctioned during the critical orbit insertion burn, causing the spacecraft to fly past Venus entirely rather than settling into orbit around it. Rather than abandon the mission, the Japanese Aerospace Exploration Agency kept Akatsuki alive in a long looping orbit around the Sun for 5 additional years, carefully managing its limited remaining fuel, until its path brought it back close enough to Venus for a second attempt using its smaller backup thrusters. An attempt that succeeded in December of 2015. Once safely in orbit, Akatsuki went on to discover several unexpected atmospheric features, including a massive, unmoving, bow-shaped structure in the cloud tops stretching across nearly the entire width of the planet's disk, apparently caused by atmospheric gravity waves generated as high-altitude winds flow up and over mountainous terrain far below. A striking demonstration of how surface topography can shape weather patterns high in the atmosphere above it, even on a planet where you might expect the surface to be almost completely disconnected from conditions in the clouds far above. NASA's Parker Solar Probe, whose primary mission focuses on studying the Sun itself, has performed multiple gravity assist flybys of Venus along the way, and during several of these flybys, its instruments detected faint near-infrared thermal emission escaping from the surface of Venus through narrow, transparent windows in the otherwise opaque atmosphere, offering an entirely new, indirect way of studying surface conditions from orbit without ever landing. Despite these valuable additions, no mission since Venera 14 in 1982 has successfully returned a new photograph taken directly from the surface of Venus. In a very real sense, Our direct visual understanding of the ground itself remains frozen at that moment, relying on data collected by a titanium sphere that melted into uselessness more than 4 decades ago. Sitting somewhere on a planet we have not physically touched again since dot. It is worth taking a step back here to consider Venus more broadly, beyond just the history of its exploration, because the planet raises a number of genuinely open scientific questions that extend well past the story of the Venera landers. Before any spacecraft ever reached Venus, scientists on Earth had already begun to unravel some of its stranger properties using a completely different technique, one that never required leaving the ground at all. In the early 1960s, researchers at large radio observatories, including facilities at Goldstone in California and later at Arecibo in Puerto Rico, began bouncing powerful radar signals off the surface of Venus and carefully analyzing the returning echo, because the leading edge of the planet, as seen from Earth, is always moving slightly toward or away from us due to its own rotation. The reflected radar signal comes back very slightly shifted in frequency, an effect closely related to the more familiar Doppler shift that changes the pitch of a passing ambulance siren. By measuring this subtle shift with great precision, radio astronomers were able to calculate Venus's rotation period without ever needing to see through its clouds optically. This work is how scientists first discovered, well before any lander confirmed it directly, that Venus rotates unusually slowly and in the opposite direction from most other planets. It stands as an elegant example of how much can be learned about a completely obscured world using careful physics and patient measurement, long before any spacecraft physically arrives to confirm the result. One of the more striking oddities of Venus involves its rotation. Venus rotates on its axis extremely slowly, taking approximately 243 Earth days to complete a single rotation, which is actually longer than the roughly 225 Earth days it takes Venus to complete one full orbit around the Sun. This means, counterintuitively, that a single day on Venus, measured from one sunrise to the next, is actually shorter than a single Venusian year, an arrangement unlike anything experienced on Earth. Venus also rotates in the opposite direction from most other planets in the solar system, a property called retrograde rotation, meaning that if you could somehow stand on its surface and watch the sky, the sun would appear to rise in the west and set in the east, the reverse of what happens here on Earth. Scientists are still not entirely certain why Venus rotates this way. Leading hypotheses involve a massive ancient collision that could have flipped or dramatically slowed the planet's original spin, or, alternatively, gradual tidal effects from the sun's gravity and the thick atmosphere, acting over billions of years to slow and eventually reverse an originally more typical rotation. Neither explanation has been conclusively confirmed, and this remains an active area of ongoing research and debate among planetary scientists. Layered on top of this unusually slow rotation is another genuine puzzle, something scientists call superrotation of the atmosphere. While the solid body of Venus itself takes 243 Earth days to complete one rotation, the thick upper atmosphere of the planet circles the entire globe in only about 4 to 5 Earth days, moving dramatically faster than the ground beneath it. This is a bit like the atmosphere of a planet spinning independently, far faster than the world it surrounds, a phenomenon not fully replicated anywhere else in the solar system in quite the same way. Researchers have proposed several possible mechanisms to explain this, generally involving complex interactions between solar heating, atmospheric waves, and the transfer of angular momentum between different layers of the atmosphere. but no single explanation has yet achieved full scientific consensus. And understanding this process remains one of the primary scientific goals of current and upcoming missions too. Venus. Venus also presents an unresolved mystery regarding its interior and magnetic field. Earth's magnetic field is generated by the churning motion of molten iron deep within its liquid outer core, a process called a geodynamo, and this magnetic field plays an important protective role, shielding the surface and atmosphere from a significant amount of damaging solar radiation and charged particles streaming outward from the Sun. Venus, despite being similar in overall size and likely similar in bulk internal composition to Earth, appears to have no significant internally generated magnetic field of its own, and scientists do not fully agree on why. One leading hypothesis suggests that Venus's core may have cooled and solidified more thoroughly than Earth's, halting the convective motion needed to sustain a but this remains difficult to confirm without direct seismic or gravitational measurements of the deep interior. And Venus's extremely slow rotation may also play some contributing role that scientists have not yet fully worked out. Venus similarly lacks any evidence of plate tectonics in the sense that Earth experiences it, where large, rigid pieces of crust slide, collide, and slip past one another over geological time, continuously recycling surface material and regulating long-term climate through processes like the carbon cycle. Instead, Venus appears to operate under what scientists call a stagnant lid regime, in which the entire crust behaves as a single, largely unbroken shell sitting atop the mantle beneath it, without the kind of large-scale horizontal plate movement seen on Earth. NASA's Magellan orbiter deserves its own mention here, since it represents the single most important radar mapping mission ever sent to Venus, launched in 1989 and arriving in orbit in 1990. Magellan spent roughly 4 years systematically imaging the surface of Venus using synthetic aperture radar, eventually mapping approximately 98% of the entire planet at a resolution far finer than the earlier Venera 15 and 16 orbiters had achieved. This effort produced the most detailed and complete global map of another planet's surface that had existed up to that point in history, revealing an extraordinary range of volcanic features, including more shield volcanoes than had been catalogued anywhere else in the solar system. Long sinuous lava channels stretching for hundreds of kilometers, and unusual circular volcanic structures called coronae, formed by upwelling plumes of hot material pushing up from deep within the mantle, a type of feature not clearly seen anywhere else. Magellan also carried instruments capable of measuring subtle variation, final atmospheric density data as it fell, before the spacecraft was ultimately destroyed by the same crushing heat and pressure that has ended nearly every spacecraft sent to visit the planet's lower atmosphere. One small but genuinely charming detail from the Magellan mapping era is worth mentioning here as well, as radar data revealed thousands of previously unknown surface features across Venus, from small craters to enormous volcanic complexes. The International Astronomical Union needed a consistent naming convention to catalogue all of them. The committee responsible settled on a distinctive rule, one applied to no other planet in the solar system in quite the same thorough way: that nearly every surface feature on Venus would be named after a woman, whether a historical figure, a goddess from world mythology, or, in the case of craters, often ordinary female first names drawn from many different cultures and languages. The one prominent exception is the tallest mountain range on the planet, named Maxwell Montes, after the physicist James Clerk Maxwell, a naming decision made before the broader convention was formally adopted, and left in place afterward as a kind of historical exception to an otherwise consistent rule. This means that, in a very literal sense, the map of Venus is a map named almost entirely for women, a fitting detail for a planet that has carried the name of a goddess since antiquity, despite this apparent lack of plate tectonics. Radar mapping, conducted by NASA's Magellan orbiter throughout the early 1990s, and subsequent reanalysis of that same data using modern computational techniques, has revealed clear evidence of extensive volcanic activity across the Venusian surface, including enormous shield volcanoes, vast solidified lava plains, and geological features suggesting some regions may have experienced comparatively recent resurfacing, geologically speaking, meaning within perhaps the last several hundred million years rather than billions. More recent reanalysis of decades-old Magellan radar images, published in the early 2020s, went further still, identifying specific surface features that appeared to have physically changed shape between two separate radar passes taken several months apart during the original mission in the 1990s, providing what many researchers consider the strongest direct evidence yet that Venus may still be volcanically active today, rather than simply having been active at some point in its more distant geological past. This remains a genuinely live and actively developing area of scientific investigation, and confirming ongoing volcanic activity conclusively will likely require dedicated future orbital missions capable of repeatedly imaging the same regions of the surface over time to directly observe any changes as they happen. Venus has also, in more recent years, become an unexpected focal point for questions about the possibility of life not on its surface, which is universally agreed to be far too hot and too high in pressure for any conceivable biology, but potentially within its atmosphere itself, at altitudes of roughly 50 to 60 kilometers above the surface, within the layer of dense sulfuric acid clouds that permanently shroud the planet. Atmospheric temperature and pressure conditions become surprisingly close to those found at the surface of Earth, sitting within a range that liquid water could theoretically exist, at least briefly, in tiny droplet form. This observation has led some researchers to seriously propose that this cloud layer could, at least in principle, support some form of extremophile microbial life adapted to an environment of concentrated sulfuric acid, a genuinely hostile setting by Earth standards, but one that certain unusual microorganisms on Earth have shown surprising tolerance for in laboratory conditions. It is worth understanding a little more about the actual composition of these clouds, since it explains why the environment is so hostile in the first place. The clouds of Venus sit in a broad layer roughly 45 to 70 kilometers above the surface, and unlike the water droplet clouds familiar from Earth's sky, they are made almost entirely of concentrated sulfuric acid droplets, formed when sulfur dioxide released from volcanic activity deep within the planet reacts with trace amounts of water vapor high in the atmosphere. These clouds are thick enough and extensive enough to cover the entire planet permanently, with no breaks or gaps of the kind that create blue sky and sunshine on Earth. Below the main cloud deck, the atmosphere remains hazy with additional layers of thinner cloud and suspended aerosol particles extending down to about 30 kilometers above the surface, below which the air becomes progressively clearer, if far hotter and denser, all the way down to the ground. Scientists have also long debated whether lightning occurs within these clouds, similar to how it occurs within storm clouds on Earth. Some spacecraft instruments, including sensitive detectors aboard the Venera landers and later missions, have recorded electromagnetic signals consistent with lightning discharges, while other missions using different detection methods have found no clear evidence for it at all. This disagreement has never been fully resolved, and the existence, frequency, and nature of Venusian lightning remains an open question that future missions carrying dedicated optical cameras capable of directly observing flashes in the clouds may finally help settle. This same middle cloud layer is also the specific region researchers have in mind when they discuss the possibility of atmospheric habitability on Venus, sometimes informally referred to as the Venus Zone, a term used to describe the narrow altitude band where temperature and pressure happen to fall within ranges that liquid water could theoretically exist, even though the surrounding chemical environment of concentrated sulfuric acid remains extraordinarily challenging for any biology built along the lines familiar from Earth. Researchers studying this question often point to certain microorganisms found in highly acidic volcanic springs and industrial waste sites here on Earth as a kind of proof of concept, demonstrating that some terrestrial biology can tolerate far more acidic conditions than most life on the planet, without claiming this proves anything definitive about Venus itself. It remains, at this stage, a serious scientific hypothesis worth testing directly, rather than an established fact, and this cautious framing matters, because it is easy for public discussion of the idea to drift toward far more certain-sounding language than the underlying science actually supports. A closely related and equally unresolved question concerns Venus's distant past, specifically whether the planet ever had a genuinely habitable early history before its runaway greenhouse effect took hold. Some climate modeling studies, including work published by researchers using NASA's own general circulation models in the middle 2010s, suggested that Venus may have had a shallow liquid water ocean on its surface for a period lasting as long as 2 or perhaps even 3 billion years, with a climate not drastically different from early Earth, before the sun's gradually increasing brightness eventually pushed the planet past a tipping point into runaway warming. Other researchers have pushed back against this picture, arguing that Venus's early atmosphere and its particular pattern of volcanic outgassing may have made conditions inhospitable to standing liquid water almost from the very beginning, meaning any greenhouse tipping point may have arrived much earlier in the planet's history, or that stable surface water may never have existed there at all in any significant, long-lived form. Resolving this disagreement matters for reasons well beyond simple curiosity about Venus's own past, because it directly affects how confident scientists can be when they estimate how long a rocky planet can remain habitable before its host, stars slowly increasing energy output, eventually pushes it into the same kind of runaway state. A question with direct relevance to Earth's own extremely distant future, expected many hundreds of millions of years from now, as well as to assessing the habitability of similarly positioned rocky exoplanets discovered around other stars. This idea gained significant public attention in September of 2020, when a team of researchers led by scientists based in Cardiff announced the detection of a gas called phosphine within the clouds of Venus, using ground-based radio telescope observations. On Earth, phosphine is strongly associated with biological processes, either produced directly by certain anaerobic microorganisms or through specific industrial processes, and no widely accepted non-biological pathway was initially known that could easily explain its presence in significant quantities within the Venusian atmosphere. This announcement generated substantial excitement within the scientific community and considerable media coverage, framed around the tantalizing possibility that this could represent indirect evidence of active biological processes occurring somewhere within the clouds of Venus. However, it is important to be clear and honest about where the scientific consensus on this question currently stands, which is genuinely unsettled and contested rather than resolved in either direction. Multiple independent research teams have since re-examined the original data and reported significant uncertainty about whether phosphine was reliably detected at all, citing potential issues with how the original radio telescope data was processed and calibrated. Other researchers have proposed possible non-biological explanations for phosphine production under Venusian atmospheric conditions, involving unusual photochemistry or volcanic outgassing processes that do not require any biological activity whatsoever. As of now, the scientific community remains genuinely divided on this question, and it stands as an excellent example of how real, ongoing scientific debate actually works: messy, contested, and not yet settled, rather than resolved neatly in either direction. Confirming or ruling out the phosphine detection, and separately confirming or ruling out any biological explanation for it, will likely require dedicated future missions carrying instruments, specifically designed to directly sample and analyze the composition of the Venusian clouds. This brings us naturally to what comes next, because after several decades of comparative neglect, largely because Mars offered scientists an easier and cheaper target for surface exploration, Venus is now entering a period of renewed serious scientific interest. With several dedicated missions currently in active development, it is worth briefly addressing a question that naturally arises once you understand the sheer difficulty involved in exploring Venus, which is simply why Mars has received so much more sustained attention over the past several decades, with dozens of successful orbiters, landers, and rovers, while Venus, a planet in many ways more similar to Earth, has been comparatively neglected. The honest answer involves straightforward practical engineering rather than any lack of scientific interest. Mars has a thin atmosphere, roughly 1% the density of Earth's, and a cold, dry surface with modest, Earth-comparable temperatures in many regions. Spacecraft sent to Mars face manageable heat and pressure conditions, allowing missions to use relatively conventional electronics, solar power, and imaging systems that can continue operating for months or even years, as demonstrated repeatedly by rovers like Spirit, Opportunity, Curiosity, and Perseverance. Venus offers no such convenience. Every single component of a Venus lander, from the electronics to the structural materials to the imaging system, must be specially engineered to survive conditions that would destroy ordinary spacecraft hardware within minutes, driving costs and engineering complexity dramatically higher for a mission that, historically, could only ever hope to operate briefly before failing. This basic asymmetry in engineering difficulty, more than any difference in scientific interest, largely explains why Mars exploration has advanced so much further than Venus exploration over the decades since the Venera program ended. And it is precisely this challenge that the current generation of planned missions is attempting to finally begin addressing again in a serious, sustained way, using modern materials science, computer modeling, and manufacturing techniques that were simply unavailable to the Soviet engineers of the 1970s, in the hope of eventually building a lander capable of operating on the surface for hours or even days. rather than the 50 to 60 minutes that marked the practical limit of the old Venera program's best efforts. It is worth pausing on a simple fact that tends to get lost in discussions of future missions. In more than 60 years of planetary exploration, only one country has ever successfully placed a functioning spacecraft on the surface of Venus and returned data from it, and that country no longer exists in its original form. The United States has never landed a probe on the Venusian surface, choosing instead across the Mariner, Pioneer, Venus, and Magellan programs to focus on flybys, atmospheric probes, and orbital radar mapping. Neither Japan nor the European Space Agency has ever attempted a landing either, focusing their efforts on orbital missions like Akatsuki and Venus Express. The extraordinary difficulty and expense of building hardware that can survive the combination of crushing pressure, extreme heat, and corrosive atmosphere found at the Venusian surface has meant that, even decades later, the achievement of the old Soviet Venera program has never actually been repeated by anyone. This is one of the more surprising and underappreciated facts in the entire history of planetary science. NASA has selected a mission called Da Vinci, an acronym describing its combined goals of deep atmosphere investigation of Venus, chemistry, and imaging, currently planned for launch before the end of this decade. This mission includes a descent probe specifically designed to fall through the entire Venusian atmosphere from top to bottom over roughly 1 hour, continuously measuring atmospheric chemistry and composition at every altitude along the way, using a mass spectrometer capable of identifying the precise chemical makeup of the air with far greater sensitivity than anything the Venera or Pioneer Venus probes carried. And critically, it will carry a modern imaging system intended to capture new photographs of the surface, specifically of a mountainous region called Alpha Regio, during the final phase of its descent, potentially providing the first new direct visual images of Venus's terrain since the Venera 14 mission in 1982. The probe is not currently designed to survive an actual landing, since its primary goal is measuring the atmosphere during descent, rather than operating from the ground itself, though mission planners have noted it may continue transmitting briefly after impact if it happens to survive, much like one of the old Pioneer Venus probes once did by accident. NASA has also selected a companion orbital mission called Veritas, intended to conduct extremely high-resolution radar mapping of the entire surface of Venus, capable of revealing far finer topographic and geological detail than the older Magellan mission achieved in the 1990s, alongside a dedicated infrared instrument designed to help determine surface mineral composition and an experiment to measure the planet's gravitational field called Envision, planned as another dedicated Venus orbiter carrying advanced radar and spectroscopic instruments, designed to work in a complementary fashion alongside NASA's Veritas mission to build the most detailed picture of Venus ever assembled, with a launch currently expected sometime in the early 2030s. Russia has also discussed a long-planned mission concept called Venerati, envisioned as a modern successor to the original Soviet Venera program, potentially including both an orbiter and a long-duration surface lander engineered to survive for hours, rather than minutes on the surface. Though the timeline and current status of this particular mission remain genuinely uncertain, having been discussed in various forms for more than a decade without a confirmed launch date. Beyond government space agencies, private ventures have also expressed serious interest in Venus, including a small privately funded mission concept aimed specifically at sending a small probe to sample the Venusian cloud layer directly during a brief descent through the atmosphere. in order to search for any organic chemical signatures that might help resolve the ongoing phosphine debate and the broader question of cloud-based habitability. Without the far greater expense of building a full surface lander, Venus also matters, scientifically well beyond questions specific to our own solar system, because it has become an important reference case in the rapidly growing field of exoplanet research, the study of planets orbiting other stars. As astronomers discover and characterize increasing numbers of rocky, Earth-sized planets around distant stars, a significant number of these worlds appear to orbit closely enough to their host star that they likely experience Venus-like runaway greenhouse conditions rather than Earth-like temperate ones. Understanding exactly how and why Venus's own greenhouse effect ran away so dramatically, using detailed measurements from a planet we can study up close, gives scientists an essential real-world reference point for correctly interpreting far more distant and far less detailed observations of these so-called hot Venus-type exoplanets, helping researchers draw a more accurate boundary between which planets around other stars might plausibly be considered habitable and which almost certainly are not, based directly on lessons learned from the world right next door to our own. This comparison has become especially relevant as space telescopes have begun directly studying the atmospheres of rocky exoplanets in detail for the first time. When astronomers detect a planet passing in front of its host star, a small fraction of the star's light passes through the planet's atmosphere on its way to Earth's telescopes, carrying faint chemical fingerprints that can reveal which gases are present. Distinguishing between an Earth-like atmosphere and a Venus-like one from this kind of data alone is genuinely difficult, since both would likely show significant amounts of carbon dioxide, and the key differences often come down to subtle details, such as the relative abundance of water vapor, the presence or absence of specific cloud layers, and the overall thickness of the atmosphere inferred from how much starlight it absorbs. Detailed models built directly from Venus's own well-measured atmosphere give researchers a genuine, calibrated reference point for interpreting these much fainter and more ambiguous exoplanet signals correctly, essentially letting scientists ask whether a distant, dimly understood world looks more like Earth or more like Venus, using real physical measurements from both planets in our own solar system as anchoring examples, rather than working from theory alone. So where does this leave our current understanding of Venus? Sitting here today, we know with a high degree of confidence that Venus experienced a genuine, catastrophic runaway greenhouse effect at some point in its history, transforming what may once have been a far more temperate, possibly even ocean-bearing world into the crushing, scorching environment we observe today. We know its surface pressure, its surface temperature, its general atmospheric composition, and we have direct, though decades old, photographic evidence of what a handful of small patches of its surface actually look like up close. At the same time, genuine and significant uncertainty remains around several important questions. We do not know with certainty why Venus lacks a meaningful magnetic field. We do not fully understand the physical mechanism driving the striking superrotation of its atmosphere. We do not know for certain whether Venus remains volcanically active today, though recent evidence increasingly points in that direction. We do not know whether the disputed detection of phosphine in its clouds reflects some unusual, purely chemical process, or something more biologically significant. And settling that question conclusively will likely take years of further study. What began as a series of destroyed spacecraft in the 1960s, each teaching engineers a small, hard-won lesson about just how wrong the accepted models of Venus really were, eventually produced some of the most remarkable achievements in the entire history of planetary exploration. A series of machines that briefly opened a window onto the surface of another world, sent us photographs, sounds, and chemical measurements from beneath a crushing, scorching atmosphere, and then quietly melted, one after another, having done what they were built to do. For more than 4 decades now, we have relied entirely on that brief handful of transmissions, from probes that no longer exist in any functional sense, sitting somewhere on the yellow, rocky plains of a world we have not physically returned to since. There is something quietly humbling in that fact, when you sit with it for a moment. We have flown spacecraft past every planet in the solar system. We have landed rovers on Mars that have driven for years, sending back thousands of high-resolution images and even short videos of dust devils crossing the horizon. We have flown a probe past Pluto, more than 5 billion kilometers from home, and received back crisp, detailed photographs of a small, icy world at the very edge of what we consider our own solar neighborhood. And yet for Venus, the planet nearest to us in size, in mass and in physical distance, closer to Earth than any other planet ever comes, our direct visual knowledge of its surface still rests on a handful of grainy panoramas, taken by machines that survived for only minutes at a time, using 1970s technology under conditions so extreme that no spacecraft sent since has attempted to repeat the achievement until now. That is finally changing, with Da Vinci's descent, Camera Veritas's high-resolution radar, and Vision's complementary instruments, and the renewed international interest these missions represent. The coming decade looks likely to produce the first, genuinely new direct information about the Venusian surface in more than 40 years. Whatever these missions find, whether it resolves the debate over ongoing volcanism, settles the question of phosphine and cloud-based habitability one way or the other, or simply adds new, unexpected puzzles to the list of things we do not yet understand about our nearest planetary neighbor, it will be building on a foundation laid by a small group of Soviet engineers who kept trying, mission after mission, failure after failure, until a titanium sphere finally survived long enough to show us what was actually down there. The next generation of images from the surface of Venus, whenever they finally arrive, will be answering questions that have quietly waited there, unresolved since 1982, and they will be doing so because enough people, across enough decades and enough different space agencies, decided that a mostly featureless, brilliant white disk in the evening sky was still worth the trouble of trying to understand properly. For now, the picture remains what it has been for more than 40 years. A handful of orange, sunlit panoramas of angular rock, a few minutes of recorded wind and drilling noise, and a long list of careful measurements taken by machines that gave everything they had before the heat finally reached them. It is not a complete picture of Venus, and it was never meant to be. It is simply the honest, hard-won beginning of one, gathered a little at a time, by people patient enough to keep trying after every earlier attempt had failed. And it is still quietly waiting to be added to.